Right from the beginning of calculus, we have been told to avoid degree, the degree measure for angles, and instead adopt radians. One reason is that we have this limit of sin theta divided by theta, as theta approaches 0 is 1, but when theta is measured in radian. And this limit enabled us to differentiate sin theta and cos theta eventually. And the derivatives came out in a very appealing manner. The derivative of sin theta is cos theta with respect to theta, of course, and when theta is measured in radian. The derivative of cos theta is minus sin theta. So as you keep differentiating either sin theta or cos theta again and again, only these things keep coming. Only there are some plus and minus. These changes are there. But say, in spite of all these conveniences that we have with radians, say still we decide to differentiate sin x degree with respect to x. What shall we get? So first of all, we of course have to express degree into radian. So that would be pi divided by 180 x radian, the sign of that, and we are differentiating it. We can do this now. Previously we could not, because we did not have our chain rule. So you apply your chain rule here. You apply the outside inside rule. So first you differentiate sin the outside room, so you get cos, nothing changes inside. So it stays pi divided by 180 x, and then you multiply that with the derivative of the inside. And when you do the differentiation, differentiating x gives you 1, and this constant of course first comes out by the constant multiple rule, and that constant actually appears here. And this, if you think of it, it is again just x degree, because pi x divided by 180 radian. So the derivative of sin x degree is pi divided by 180 times cos x degree. So we are actually again getting cos x degree, but with this somewhat not so nice coefficient. And now you can imagine that if you keep differentiating, this will only get worse and worse, because its higher and higher powers will appear. So for this reason also, radians, that measurement is what we prefer. So that is example 7. And finally there is one more example, example 8, where we are going to see how we can use the chain rule for differentiation to model a cube, an ice cube which is melting. We want to know how long it will take for the cube to melt completely, disappear. And the example is just that question: how long will it take an ice cube to melt? The solution starts by erecting a mathematical model for solving the problem. You see, it's a real problem in the sense that it's a physical problem, a problem that is about the real world. It's not a mathematical problem in the sense that it's not just about mathematics, it's about physics, a physical situation. And whenever you try to model something in the real world, whether that something is physical, chemical or biological, you have to have some kind of assumptions which are actually approximations. Nature is so complex. In fact, any small part of it is so complex. So many different things are affecting what you are trying to understand from different sides in so many different ways that it's nearly means actually it's impossible to take into account everything. And if you somehow manage to take into account nearly everything, then your mathematical model will be so complicated that it will be useless, because the equations you will get will be intractable. You won't be able to solve them. So of what use are they? That is why we have to, in the beginning, start with some assumptions which are approximations. These approximations may sound really, far-fetched in the sense that they may sound like they are really watering down the situation to an extent where the resulting model would not really describe what is going on. However, that's the best you can do. You do whatever you can do and hope for the best. The first assumption itself looks unrealistic. As the ice cube melts, it retains its cubic structure perfectly. You can understand that this assumption is not a very good assumption if the heat is too much. You just think of something, say a block of ice. If you are really applying too much heat to it will melt quickly, and as it does so, it will lose shape. It will become deformed, it will go here and there, and eventually, of course, it will vanish, but as it does so, it will lose shape quickly. But if the temperature is not really that much, and say the melting is slow, and there is not much heat, there is no clear source of it that is being applied. Say it is just left outside and it is slowly melting, and as it does so, it more or less retains its cubic shape. So that is the first assumption. By doing so, we are deviating from reality, but not by much. Okay. So whatever we are going to get as a result of this approximation or simplification will more or less tell us what's really going on. Alright. So now with this assumption, we can next consider this. Let S be the side length at any given time. And side length now makes sense because the cube will stay cube even if it diminishes in size. So this S will change with time. And if S is side length, then volume of course is S cube. Now comes the next assumption. Both volume and side length are functions of time, okay, but differentiable functions of time, so that we can bring in derivatives and do something with them. But there are other assumptions also. So the third assumption is this. The cube's volume decreases at a rate that is proportional to the surface area of the cube. And that translates into this equation, this differential equation. This is the rate of change of volume with respect to time. A differential equation is just an equation which involves derivatives. At this stage, let's just think of it that way. And forget about differential equations. This is just an equation involving the rate of change of volume with respect to time. dV dt is the rate at which volume is decreasing with time. And what are we saying? That rate is proportional to the surface area of the cube. So a cube has 6 sides. Each side is a square of area s square because side length is s. So 6s square is the total surface area. And V is proportional to that. More surface area means more rapidly the volume is changing. In what sense is it okay to consider this condition? You see, melting happens first at the surface, right? On the surface. From there only, the molecules which are nearest to the atmosphere, they will first go out of the cube, and that's what melting is. So that is why it's more or less reasonable to make this assumption. The negative sign indicates that volume is decreasing with time, so the rate is negative. And this K is constant of proportionality. And here actually there is inherent in this K is another, I should not say approximation, but another restriction. We are assuming K to be a constant. That may not be. And actually this constant K itself may change depending on the situation. For example, temperature, pressure, there are many things, humidity in the area in which the cube is placed. But taking into account all those things, say this is how I am modeling the melting. And that's not enough. We need to know something else also. Suppose through physical experiments this was found. Suppose the cube loses 1/4 of its volume in the first hour of melting. So these are the things we have with us. V equals S cube, that condition dV dP equals minus 6Ks square, where K is the positive constant. And there is an initial volume, the volume of the cube that we start with when the melting has not started or is just starting. At t equal to 0, when time is 0, the initial volume is V0. And after 1 hour, 1/4 of the volume was lost. That means 3/4 is remaining. So what we next do, we differentiate both sides of that equation, V equals S cube, with respect to time using chain rule. And when you do that, you get dV dt equals, so this side was S cube, the derivative of S cube with respect to time has to be done using chain rule. So you first differentiate S cube as if it's just a cube, so that way you get 3S square. That means you differentiate the outside room, and then you differentiate the inside room, that is S, with respect to time. So you get this. But already a part of your entire assumption, those, what do you call it, model, that tells you that dV dt is minus 6Ks square. So from that, after cancelling things from both sides, you get this ds dt equals minus 2K. I am writing ds dt on this side, and this is constant. So what is this? This is the rate of change of side length with respect to time. The side is shrinking with time, and that is why there is a negative sign. So the side length is decreasing at the constant rate of 2K per hour. Once you say decreasing, there is no need to write that minus sign. That's understood. And that is why if the initial side length is S0, there would be some side length with which the cube starts. Then the side length S1 after 1 hour of shrinking is S1 equal to S0 minus 2K, because that is the rate at which it is decreasing. And that implies 2K is S1 minus S0. Now we consider another thing. If 2K is the rate at which the cube is, the side length is decreasing per hour, then the melting time is related to the initial side length by this equation, obviously. 1 hour goes and 2K length is lost. So in T hours, if everything has to be lost, then 2K times T should be equal to the entire length, obviously. And from that, we can get a formula expressing T melt, the melting time, in terms of this 2K and S0, S0 divided by 2K. And when you use this, you get this, S0 divided by S1 minus S0. Now what are we going to get from this? I made a small mistake in writing that relation. It's actually 2K equal to S0 minus S1, not S1 minus S0. Because S1 is less than S0. S0 is the initial length, and then it decreased to S1 in 1 hour. So accordingly here also not S1 minus S0, S0 minus S1. And then you can see that if you divide both the numerator and denominator by S0, this is what you get. Now you think of this ratio S1 divided by S0. S1 is the side length after 1 hour, but after 1 hour the volume was how much? 3/4 of V0, and side length is cube root of volume because volume is side length cube, and the initial side length of course is related to the initial volume like this. Side length S naught is equal to the cube root of V naught. So you can see that there is a cancellation. And after you cancel the cube root of V naught from the numerator and denominator, you are left with the cube root of 3 divided by 4, which is approximately equal to 0.91. And so you can now use this for calculating your T melting time. That now equals 1 divided by 1 minus 0.91, which is approximately 11 hours. So after that initial melting of for 1 hour, the cube takes 10 more hours to melt away completely.